Now we're going to start talking about statistics for real. And we do so by linking probability distributions with observations using sampling distributions. A population for us, it's going to be a set of similar items and items that you're experimenting or measuring things about. So population could be like, say, all the inhabitants of a country, or all the students in a classroom, or all possible widgets that are being produced by a production line. It's going to be sometimes possible to observe the entire set of observations that make up a population, right? If you lived in this country long enough, you might have had to fill a census form. So technically speaking, here the entire population is being measured by the census. But there's going to be cases where you can't do that. There's just too many items in the population. And if you want to be able to say something about the population, you need to sample it. You need to find a subset of the population and then do the measurements on that subset. Whenever polls are published for elections, it isn't that we couldn't get the full population voting intentions. I mean, if you think about it, the election day itself, that is the census. That's when you query the entire population. But when you prepare a poll, you're trying to get a sense as to what the population as a whole will say or do by only polling or sampling a small subset of them, 500, 1,000 of them. And if you've been following elections recently, you know that polling is actually quite difficult, right? If the subset that you pick to represent the population as a whole is not representative in some way, then the inferences that you make about the population as a whole might be off. It could be off a little bit, or it could be off quite a lot. So we're going to consider x1 all the way to xn as n independent, and this is important, independent random variables, and each of them will have the same distribution f, say. That means that they're identically distributed. Now notice here we're using uppercase letters to describe the random variables themselves. Lowercase letters will be reserved for observations of the random variables. The set x1 to xn is a random sample of size n from the population that has a distribution function f. And now we come to the statistics part of things. Any function of a random sample is a statistic of the sample. And the probability distribution of that statistic is called its sampling distribution. Before we go on to talk about this a little bit more, let me remind you that we have some properties of expectation and variance. The expectation of a constant plus a random variable multiplied by some scalar is the constant plus the scalar multiple of the expectation of the variable. So this is one that we need to know. We need how to separate expectations when we have a linear combination of terms. The variance has its own rule. It is not a rule that follows the same pattern as the expectation, right? Variance, if you add a constant term, it doesn't change anything to the variance. And if you have a scalar multiple here and you get it out, you need to take the square. And the standard deviation, and it's just the square root of the variance. So if you remember the rule for the variance, it's easy to derive the rule for the standard deviation. If you have two independent random variables, you can say a few things about them. Well, first of all, whether they're independent or not, the expectation of two variables x and y, the sum of two variables x and y, it's simply the sum of the expectations. So this works like a lot of things you would expect. It works like differentiation, it works like integration. This is a nice linear property. If on top of that, and only on top of that, if on top of that your random variables are independent, then the sum of the variances is equal to the variance of the sums. But that's only the case if they're independent. If they are not independent, there's an added term here. you have to add twice the covariance of x and y. When it turns out that the variables are independent, the covariance is 0. This disappears. Now, we have not defined the covariance, and in this course we will not be defining the covariance. We'll talk about correlation a little bit in chapter 7. That's linked to the definition of covariance, but we're not talking about covariance here. This rule can be extended if you have more than 2 random variables. So if you have n random variables and they're all independent, then the expectation of the sum of these random variables will be the sum of the expectations, and the variance of the sum will be the sum of the variances. But again, let me reiterate, this is only true if they are independent random variables. Just to remind you what we mean when we talk about independent random variables, imagine for instance that xi is the result of the toss of a coin by person I. So you give everybody a quarter. They all go to different locations and they flip a coin. And x1 would be, heads or tails, depending as to whether person 1 flipped heads or tails, and so forth. Now, if all of these coins are independent of one another, they haven't been produced in the same location, or you're not using the same coin over and over again, then you can assume that the experiments are independent, and so the random variables will also be independent. So what I've described there basically is a special case of the situation where you have n independent random variables. If all of your random variables have exactly the same distribution, same cumulative distribution function, here's what we mean, then we say that they're independent and identically distributed. And that's a bit of a mouthful, so we'll say IID. So whenever we say IID, what we're assuming is that each variable has the same distribution as all the other ones. In particular, they have the same mean and the same variance, and they're all independent from one another. So you can imagine a situation where each experiment is done in a separate location by different people using different material, prepared to the same specifications, mind you. So if you have n random variables that are IID, and the expectation for each of them is mu, that's their mean, and the variance for each of them is sigma squared, that's their variance, then the expectation of the sum of the variables, by the rule we've seen previously, that's going to be the sum of the expectations, but each expectation is a constant, mu, so you're adding mu together n times. There's your n times mu right here. When you play the same game with the variance of the sum of IID variables is going to be n times the variance of one of them, so n times sigma squared. Here's an example. You have a random sample of size n equals 100. You take it from some population, and the thing you're measuring in the population as a whole has a mean of 50 and a variance of 0.25. So n is 100, mean 50, variance 0.25. What's the expected value and the variance of the sample total? So what you need to be able to understand here is that this problem actually translates to the following statement. If x1 to x100 are IID with an expectation, which is the constant mu, which happens to be 50, and a variance, which is sigma squared, 0.25 for every single one of the random variables, find the expectation of the total and the variance of the total, where the total tau is the sum of these variables. But you simply use the IID formulas, right? I mean, you know what the expectation of the sum of random variables would be. It would be n times the expectation of each of them. So 100 n times mu, it's 5,000. And the variance in that case would be n times sigma squared, so 100 times 0.25, which is 25. What this is saying is that when you pick 100 observations from your population, assuming that the mean value is mu, you would expect, on average, that the sum of the 100 observations you've taken will be 5,000. And the variance in this choice will be 25. Here's another example. We're interested in the weights of potting mix bags. Now, their mean value can be 5 kilograms, but you know as well as I do that they can't all be exactly 5 kilograms, even though it says 5 kilograms on the bag. There'll be some variance, some variation in weights. So we'll say the standard deviation is 0.2 kilograms. You go to the shop, you purchase 4 of these bags. We assume they've been selected independently from stock. That might not be a very realistic assumption to make here, but let's assume that that's what actually happened. What's the expected value and the standard deviation of the total weight carried? There's a population in there which is implicit. All of the bag weights, not just the ones that you're going to be selecting to bring home with you. Right? So there's 4 bags. They're going to have weights X1, X2, X3, and X4. And these, by assumption, are IID because they've been selected independently. And the mean, the expectation of the weight, is the mean value in the population, which is 5 kilograms. And we've said that the standard deviation is sigma, 0.2. Sometimes we give these problems with variances, sometimes we give them with standard deviations. So if we know that the standard deviation is 0.2, what this tells us is that the variance is actually 0.2 squared, 0.04. So now the total will be the sum of the weights, so x1 plus x2 plus x3 plus x4, that's how much the combined 4 bags will weigh. And if you use the formulas that we've seen, the expectation of the total, the expectation of the sum, will be the sum of the expectations. So because these are IID, they all have the same mean, so each of the expectations are the same, n times mu. And in this example, n equals 4, mu equals 5, so the expectation is 20. And you use the same formula for the variance. So n times sigma squared, 4 times 0.04, 0.16. Be careful on a multiple choice question. Another option here for the variance would be 4 times 0.2 to make sure that you're remembering what you're supposed to use. So if you're looking for the standard deviation of the total weight carried, you need to take the square root of the variance. The square root of 0.16 is 0.4. Now we can revisit the sample mean. The sample mean is a function that you compute with your random variables in the sample. You are literally adding them up and dividing by the number of observations in the sample. That is a statistic. That's usually the statistic that people are interested in. That's not the only one you can be interested in, but that's one of the things you can be interested in. If your random variables are all IID, with mean mu and variance sigma squared, then you can also compute the expectation of the mean. And now you have to be careful. The expectation of the mean is not in general going to be equal to the expectation of the total, which was the sum, right? Because we have this extra term here, 1 over n. It shows up in here. It's a constant, so we can get it out of the expectation operator. We have 1 over n times the expectation of the total. We know what the expectation of the total is. According to the IID formulas, it's n times mu. And now we have, though, 1 over n that multiplies n times mu. The n's cancel out, and you end up with mu. The expectation of the mean, so the expectation of the statistic, which is the mean, is the same as the expectation of each of the observations. And the variance, again, you can't just use the variance of the total. It's in general not going to be equal because, once again, you have a factor of 1 over n here. What happens when you have a constant in front of a random variable? You need to get it out and square it for the variance. So 1 over n squared times the variance of the total, and we know what that is from the formulas n sigma squared. So now when we do the cancellation, this n cancels out with one of the n's here, and you're left with sigma squared over n. And that, however, is not the same as the variance of xi. The variance of xi, that's sigma squared. Okay, so the variance of the mean is in general smaller than the variance of each observation. What this is saying is that if you're trying to estimate the mean, you will in general have less spread in its values. So if you take n observations from the population, you compute its mean. That gives you one estimate for the mean. Great. Now you take n other observations. Perhaps there is some overlap. You get another estimate for the mean. You do this a third time, a fourth time, a fifth time, and so forth. Each of these is an estimate for the mean. If you want to get a better estimate for the mean, you can just do the average of all of these estimates for the means. Great, you'll get a nice estimate for the mean. But if you look at the variance in all of these mean estimates, it is not very large, or at least not as large as the variance in the measurement of one such observation, right? So if you are trying to estimate the mean, you get different formulas here. Let's see if an example makes this easier to understand. You have a set of scales. They will return the true weight of the object that you're weighing, but there's a random error term in it. And the random error has mean 0 and standard deviation 0.1. What this means is that sometimes the weight that is being returned by the scale is above the true weight, sometimes it's below the true weight. And the difference between the true weight and what's being reported has a standard deviation of 0.1. What's the standard deviation of the average of 9 measurements of an object? So each measurement alone has some deviation from the true weight, but if you take 9 such measurements and you average them out, how does the average of the 9 reported weights differ from the average, the true average of the 9 weights, the average of the 9 true weights? So we'll just look at one object here that is being measured 9 times. So let's say that the true weight is mu. The random error basically tells you that whenever you measure the object, you will get something like mu plus zi. Xi, that's the measurement that is being returned by the scale. Mu is the true weight, unknown, and zi is the noise, the deviation. Call this the residual from the true weight. And what the problem is telling you is that the expectation of that noise, that random error, is 0 and its standard deviation is 0.1. And assuming that you have independent weighings, then the ZIs are IID. This is an assumption you have to make if you want to be able to answer this question. If the ZIs are IID, then so are the XIs. Now the expectation of the XIs will be mu. It's not 0 anymore because it's whatever mu would be. And the standard deviations would still be 0.1. Here you can get that answer by applying the properties of linear combinations of random variables. Now you take the average of 9 measurements, so n equals 9, and that gets you the sample mean x bar. The expectation of that sample mean is mu. We saw this formula on the previous slide. And the standard deviation would be the square root of the variance. Just write that down here. And the variance itself is sigma squared divided by n. Take the square root, you end up with sigma divided by square root of n. We know what sigma is. It's 0.1 divided by the square root of 9. You're dividing by 3. So 0.1 divided by 3 is the same as 1 over 30, about 0.033. So we have found here the standard deviation of the average of 9 measurements. And you'll notice that it is smaller than the standard deviation of a single measurement. We don't know the distribution of the XIs. We don't know what the value mu is. We don't even know what family of distributions it comes from. Is this normally distributed? Is this exponentially distributed? Is this a gamma? We don't know. All we know is the mean and the variance. There's another interesting case when you have independent normal random variables on the same experiment. So what you're saying here is that each measurement is drawn from a normal distribution with a given mean mu I and a given variance sigma I squared. Now, if all the XIs are independent, we already know that the expectation of the total, of the sum, will be the sum of the expectations. in this case mu1 plus mu2 plus mu3 all the way up to mu_n, and the variance of the totals will be the variance of the sum, which is the sum of the variances because they're independent here, and that would be sigma 1 squared plus sigma 2 squared plus all the way to sigma n squared. If the xi's are all normally distributed, this is where something interesting happened. The total is also normally distributed, and it has a distribution which is given by the following parameters. The mean of the total will be the sum of the means. The variance of the total is the sum of the variances, but these parameters here are actually the parameters of a normal distribution. There was no guarantee that this was going to be the case. The expectation of the total is always the sum of the means, and the variance of the totals is always the sum of the variances. But the fact that these are the parameters of the normal distribution, so that the total is normally distributed, we didn't know that this was going to happen. This is only the case exactly if the original measurements were also normal to start with. Now, mathematically, what this is saying, we know this, if you have a random sample from a population with mean mu and variance sigma squared, the expectation is n mu, the variance is n sigma squared. Well, the expectation of the total, the variance of the total, the expectation of the mean is mu, the variance of the mean is sigma squared n. Again, this is true no matter what distribution the original measurements followed, but if the population distribution is normal, if they're IID here, and each one of them comes from the same normal distribution, then the total and the sample mean are also normal, and they follow these distributions here. This one in particular will be very important when we talk about the central limit theorem. We'll do one final example. You have a population of students' weights, and let's say it's normal with a mean of 75 kilograms and a standard deviation of 5 kilograms. If you pick 16 students at random in the classroom, and you assume that you've done this independently, what's the distribution of the random total weight, tau, the sum of the weights? What's the probability that the total weight will exceed 1250 kilograms? So you pick 16 students. The measurements will be x1, x2, x3, all the way up to x16. They are IID and follow a normal distribution with mean 75 kilograms and variance 25. Remember, right? Standard deviation, variance is the square of that. So here we have a mu and a sigma squared. The sum tau will also be normally distributed according to what we've just seen, and it will follow a normal distribution with mu times n, 75 times 16, and variance sigma squared times n, 16 times 25, so basically 1200 and 400. Now you can standardize that by subtracting the mean and dividing by the square root of the variance, by the standard deviation, and this mu z is going to follow a standard normal distribution. So if you want to know the probability that tau is greater than 1250, that's going to be the same thing as the probability that z is greater than 1250 minus 1200 divided by 20. These numbers here are not random. This is where they come. That's the same thing as computing the probability that z is greater than 2.5. That should be a pretty small probability. If you use a table, that's 1 minus the probability that z is smaller than 2.5, which is basically 1 minus 0.99, some decimals, 0.0062. So there's a very, very small chance that if on average each student weighs 75 kilograms and there's a standard deviation of 5 kilograms, that the total sum for these 16 students would be greater than 1250.